Dear students, in this video we will talk about Lossen rearrangement. Lossen rearrangement is conversion of O-acyl hydroxamic acid derivatives to corresponding isocyanates. So this is Lossen rearrangement, and general equation is this is O-acyl hydroxamic acid, and in the presence of heat and base, this can be converted into isocyanate. This rearrangement was reported by Wilhelm Lossen in 1872, and he was working on the pyrolysis of benzhydroxamate and he observed the formation of benzoic acid and phenyl isocyanate. This is benzoyl, benzhydroxamate, and when this compound is heated, it converts into benzoic acid and phenyl isocyanate. Wilhelm Lossen observed this pyrolysis, and few years later he also observed that when potassium salt of any soil benzhydroxamate is treated with water and heating conditions, it gives diphenylurea derivative and CO2 is also liberated, and potassium anisole is also formed. This is potassium anisolate. This AR group represents anisole. So this is general structure, and specifically he was working on anisole derivatives of this compound. And if we see, this is called O-acyl derivative. And why it is called O-acyl derivative? Because this acyl group is present on oxygen. So when this acyl group has been installed on oxygen, it would be called O-acyl derivative. And why it is called hydroxamic acid? Because the general structure of hydroxamic acid is this one. This is hydroxamic acid, and in general hydroxamic acid cannot undergo this conversion, and we have to convert it into a suitable leaving group. Or we have to make it activated in order to bring about this transformation. Therefore, we prepare the derivatives which undergo this reaction. Furthermore, this group is called benzoyl group. So we should be able to differentiate between benzyl and benzoyl. Benzoyl is phenyl group attached to carbonyl group. This together is called benzoyl. The presence of this group is mandatory. And benzyl group is this one. This is benzyl. And this is abbreviated as BZ or BZ, and this is abbreviated as BN. So we should know the difference. Now we see the mechanism of the reaction. So in the first step, we treat it with a base, and for example the base is hydroxide, any alkali, for example sodium hydroxide or potassium hydroxide. So proton would be abstracted from here because the presence of this group makes it hydrogen acidic, and this is removed, so we will get this one. Now we have negative charge on nitrogen, and in this case when two electronegative atoms are joined together, the molecule is generally unstable, and this group would migrate with its electron pair towards nitrogen. This would be eliminated, and this negative charge we can show on this side. This would come here, and as a result we will get this isocyanate, and this isocyanate is formed through this bridged anion. So this bridged anion then converts into this isocyanate, and we get this as well. So here we can see the bond formation and bond breaking is taking place in a single step. So this is a concerted reaction, and this bond is breaking. We can see we have shown the dotted bond here, which represents the breaking of the bond, and here a new bond is formed along with this one. So this bond has been represented here, and here this bond is breaking, so we have shown here with dotted bond, and this carbon is making a new bond with nitrogen. So a new bond with nitrogen has been shown with dotted bond. So in the end we get the isocyanate. If we use potassium here, for example, we would get potassium here as well. So this is the Lossen rearrangement, and here we can see the migrating group is taking electron pair along and migrating towards electron deficient nitrogen, and this group is moving with electron pairs, so nitrogen becomes electron deficient. As a result, this rearrangement is the migration towards electron deficient nitrogen, and in this case we can see from this bridged anion that retention of configuration takes place. So this rearrangement proceeds via retention of configuration, because we can see the chiral center, if this is a chiral center, it is attached to carbonyl group, and during bond breaking and bond formation, or we call it transition state, this is also attached to nitrogen, so the configuration remains the same. All the groups on this carbon do not change their configuration. As a result, retention of configuration takes place. Okay, now we see the preparation of O-acyl derivatives of hydroxamic acid. In the first step, we use acid chloride, which is allowed to react with hydroxylamine, and in this case this would attack here, and because acid halides belong to class 1 carbonyls which have acyl group attached to electronegative atom and can undergo nucleophilic substitution reaction, so this would attack here, this pi bond would break, and as a result tetrahedral intermediate would form. The negative charge would come back due to back donation of oxygen, and this would be eliminated, and as a result finally we would get hydroxamic acid. And we have just discussed that hydroxamic acid cannot undergo this rearrangement. We have to convert it into O-acyl derivatives, or we have to activate this group. So we have to add acid chloride in the presence of base. So as a result we would get O-acyl derivative. We can also use here sulfonyl chlorides as well. For example, methyl group, methane sulfonyl chloride, which is CH3 SO2Cl, or para-toluene sulfonyl chloride. And both of these are good living, form a good leaving group. So if we use sulfonyl chlorides, we can also get these derivatives. So these can also undergo Lossen rearrangement under suitable conditions. So this was the preparation of O-acyl derivatives of hydroxamic acid. This is one way. We can also use carboxylic acids. Carboxylic acids can be converted into acid chloride using thionyl chloride, for example, and which can undergo further transformation as shown here. We can also use esters and directly react the esters with hydroxylamine hydrochloride, but esters are not so reactive, and acid chlorides are better in terms of reactivity with hydroxylamine hydrochloride, and as a result we can get these O-acyl derivatives of hydroxamic acids. I hope this is clear to you. Now we see the reactivity of isocyanates. This is isocyanate, and in this case we can see this carbon has been attached to two electronegative atoms. This nitrogen is electronegative, this oxygen is electronegative. As a result, this gets partial positive charge and becomes electrophilic in nature. Therefore, nucleophiles can attack on this carbon, and for example, water. The lone pair present on oxygen in water can attack on this carbon, and this bond can break, and as a result we get this molecule, and here oxygen has positive charge and here we have negative charge on nitrogen, so this negative can take this proton, and as a result we would get this molecule. This is called carbonic acid. Carbonic acid is an unstable acid. This molecule is unstable, and there are very good chances of liberation of this CO2 from here, and as a result CO2 can liberate if this molecule is heated, and we get RNH2. When CO2 is removed, this bond shifts here and this bond takes this proton, so we get primary amine. So if isocyanate is allowed to react with water and is heated, we get primary amine as product. And if it is allowed to react with amine, and again in this case nitrogen has lone pair which can act as nucleophile, and it would attack here as well. This bond would shift here and we would get this molecule, because we have nitrogen here which was neutral, and in neutral condition it used its electron pair, the lone pair, to form a bond with this carbon. Therefore, when an atom in neutral state gives away electron pair, it gets positive charge. So nitrogen has positive charge here, so this proton would be taken by this nitrogen, these electrons would shift here, and as a result we get this one. This is called urea derivative. And with the name of urea in mind, we can recall that Frederick Wöhler was the first scientist who reported urea. So this is urea derivative, and in the end if we treat it with, for example, alcohol, ROH. Again, alcohol has oxygen having lone pair. This lone pair would be used to attack on this carbon, which is electrophilic in nature, and as a result of this attack we would get this molecule, and similar mechanism would be adopted and we would get this one. Earlier we saw that RNH COOH is called carbonic acid, and this is analogous to a carboxylic acid. And for example, a general acid would be acetic acid, and if this hydrogen is replaced by an alkyl group, we call it, for example, ethyl. So this molecule is called ethyl acetate. I write it here as well. So we call it ethyl acetate. Similarly, we have alkyl group here. So this would be called alkyl carbamate. So when isocyanate is treated with water, we get carbonic acid. And when isocyanate is treated with alcohol, we get alkyl carbamates or carbamates. And when isocyanate is treated with amine, we get urea derivatives. So isocyanates are very important synthetic intermediates which can be used to bring about a lot of organic conversions. And if water is used, we get carbonic acid, which is unstable acid and loses carbon dioxide to form primary amine. And if it is treated with alcohol, so we get carbamates as product, and if it is treated with amines, we get urea derivatives. I hope this is clear to you. If you have any questions or any confusion, please leave your comments in comment box. Thanks.